We are immersed in them, these invisible waves. They are all around us, constantly flowing through the air, unseen but ever present. Every time we make a call, send a text, or browse the internet, we are tapping into this invisible ocean. They carry energy, information, and even life itself. These waves are the backbone of our modern communication systems, enabling everything from satellite transmissions to wireless energy transfer. They are the silent carriers of our voices, our data, and our digital lives. Electromagnetic waves, from radio waves to gamma rays, make up the fabric of our universe. They span a vast spectrum, each type of wave with its own unique properties and uses. From the low-frequency radio waves that bring us music and news, to the high-frequency gamma rays that reveal the secrets of the cosmos. But where did our understanding of these waves begin? The journey of discovery started centuries ago with curious minds and rudimentary tools. Early scientists and philosophers pondered the nature of light and magnetism, laying the groundwork for future breakthroughs. We owe a great debt to James Clerk Maxwell, a Scottish physicist who in the 19th century unlocked one of the universe's greatest secrets. His groundbreaking work in electromagnetism revolutionized our understanding of the natural world. He unified electricity and magnetism. Maxwell's equations elegantly described how electric and magnetic fields interact, showing that they are not separate forces but interconnected phenomena. Join me as we journey from the classical age of physics to the quantum realm, exploring the origin and fascinating behavior of electromagnetic waves. We'll trace the evolution of scientific thought, from the early experiments of Faraday and Hertz to the modern applications that power our world today. Maxwell's equations, a set of elegant formulas, showed that electricity and magnetism are not separate forces. These equations are the cornerstone of classical electromagnetism, encapsulating the fundamental principles that govern the behavior of electric and magnetic fields. They are two sides of the same coin. This profound insight revealed the true nature of electromagnetic waves, uniting previously disparate phenomena under a single theoretical framework. And from this union, a profound prediction arose: the existence of electromagnetic waves. Maxwell's theory suggested that these waves could propagate through space, carrying energy and information across vast distances. These waves, Maxwell theorized, are disturbances in the fabric of space and time. They ripple through the cosmos, much like waves on the surface of a pond, connecting distant points in the universe. They travel at a specific speed, a speed we now know as the speed of light. This constant speed is a fundamental property of the universe, shaping our understanding of space, time, and the nature of reality itself. Maxwell's equations are the foundation of our understanding of light and other electromagnetic waves. They describe how electric and magnetic fields interact and give rise to these waves. Imagine a still pond. Now imagine dropping a pebble into it. The pebble creates ripples, waves that travel outward from the point of disturbance. Electromagnetic waves are similar. A disturbance, perhaps a change in an electric current, creates ripples in the electromagnetic field. These ripples or waves propagate outward, carrying energy with them. Maxwell's brilliance was in predicting their existence and calculating their speed. He found that they travel at approximately 299,792,458 meters per second in a vacuum. This speed, the speed of light, is one of the fundamental constants of the universe. For centuries, scientists debated the nature of light. The question of whether light is a wave or a particle has intrigued and puzzled some of the greatest minds in history. Is it a wave like ripples on a pond? This wave theory was supported by the way light can spread out and interfere, creating patterns much like water waves. Or is it a stream of particles like tiny bullets? This particle theory was bolstered by experiments showing light traveling in straight lines and casting sharp shadows. The answer, as it often happens in science, turned out to be more complex and fascinating. Light doesn't fit neatly into one category or the other. Light, we now know, exhibits a dual nature. It can spread out and interfere like a wave, but also travel in discrete packets. It can behave as both a wave and a particle. This duality is not just a theoretical concept, but has been demonstrated in numerous experiments. This wave-particle duality is one of the cornerstones of quantum mechanics. It challenges our classical intuitions and requires a new way of thinking about the nature of reality. Albert Einstein, in his groundbreaking work on the photoelectric effect, showed that light can behave as discrete packets of energy, called photons. This was a pivotal moment in the development of quantum theory. These photons, although massless, carry energy and momentum, exhibiting particle-like behavior. They can knock electrons out of atoms, demonstrating their particle nature. Quantum electrodynamics, or QED, a theory developed in the mid-20th century, reconciled the wave and particle aspects of light. It provided a comprehensive framework for understanding how light and matter interact. QED describes light as a quantum field, a fundamental entity that permeates all of space and time. This field can be thought of as a sea of possibilities, with photons being the ripples on its surface. This field can exist in various states of excitation, and these excitations are what we perceive as photons, the particles of light. This elegant theory not only explains the dual nature of light, but also unifies it with the other fundamental forces of nature. Light, in its various forms, interacts with matter in fascinating ways. These interactions give rise to phenomena we experience every day. When light encounters a smooth surface like a mirror, it bounces back, a phenomenon we call reflection. This is why we can see our reflection in a mirror. Refraction occurs when light passes from one medium to another, like from air to water. The speed of light changes in different mediums, causing the light to bend. This is why a straw in a glass of water appears bent at the waterline. Diffraction is the bending of light waves around obstacles or through narrow openings. It explains why we can hear someone talking around a corner even if we can't see them. The sound waves diffract around the corner, reaching our ears. Polarization is another intriguing property of light. Light waves can vibrate in different directions. Polarization refers to the direction of these vibrations. Sunglasses, for example, often utilize polarizing filters to reduce glare. These filters block light waves vibrating in certain directions, reducing the intensity of light that reaches our eyes. Light, while behaving predictably in our everyday lives, reveals even more fascinating behavior in extreme environments. Near black holes, objects of immense gravity, light is bent and warped to an extreme degree. This warping of space-time, predicted by Einstein's general theory of relativity, creates a phenomenon known as gravitational lensing. Black holes act as cosmic lenses, bending and magnifying the light from objects behind them. This allows us to see objects that would otherwise be hidden from view. As we delve into the future, the role of light in shaping our world becomes increasingly significant. The study of light continues to push the boundaries of science and technology, opening new frontiers and possibilities that were once the realm of science fiction. In the realm of quantum computing, where the very fabric of reality is manipulated, scientists are exploring the use of photons, the particles of light, to create incredibly powerful computers that could solve problems beyond the reach of classical machines. These quantum computers have the potential to revolutionize fields such as medicine, material science, and artificial intelligence, offering solutions to complex problems and driving innovation. Imagine a world where diseases are cured with precision, materials are engineered at the atomic level, and AI systems operate with unprecedented efficiency. This is the promise of quantum computing. Metamaterials, a groundbreaking innovation in material science, are artificially engineered materials with unique electromagnetic properties that can manipulate light in extraordinary ways. These materials offer another exciting avenue of research, with the potential to transform various industries. These materials can manipulate light in ways not found in nature, leading to potential applications such as invisibility cloaks, super-resolution imaging, and advanced optical sensors. Imagine a world where objects can become invisible, where imaging technology can see beyond the limits of current devices, and where sensors can detect the faintest of signals. This is the future metamaterials promise. The cosmic microwave background radiation, a relic from the dawn of the universe, the faint afterglow of the Big Bang, provides a glimpse into the early universe, offering clues about its origins and evolution. By studying the properties of this ancient light, cosmologists can piece together the history of the universe and understand its evolution, from the Big Bang to the present day. This research not only helps us understand the universe's past but also its future, shedding light on the fundamental forces that shape our cosmos. Cosmologists can use this information to predict the future behavior of the universe, providing insights into its ultimate fate. From Maxwell's groundbreaking equations which unified electricity, magnetism, and light, to the mind-bending world of quantum mechanics, where particles can exist in multiple states at once, our journey through the world of light has been nothing short of extraordinary. Light has been a constant companion in our quest for knowledge. The study of light has not only illuminated the nature of the universe but has also paved the way for countless technological marvels that have transformed our daily lives. From the screens of our smartphones to the fibers that carry our internet, light is at the heart of modern technology. As we continue to probe the mysteries of light, we can be sure that even more fascinating discoveries await us, discoveries that will undoubtedly shape the future of science and technology for generations to come.